So if this is minus 13, add 13 to both sides, and you get q is equal to 13. Now the question is find the value of p and the value of q. We've done it, but I could write down a bit nicer. F of z is z squared plus p times z is minus 6z plus q is 13. Right. There is another way of attacking this problem. So if the roots, if the coefficients are what are called real numbers, then there's something called the conjugate root theorem. Conjugate root. And what the conjugate root theorem says is that if f a polynomial, so polynomials are sums of powers of z, like this one. Let's write z is a poly with real coefficients. So the coefficient of z squared is 1, that's a real number. P and q, in the question are real numbers. So this is a polynomial with real coefficients. Then z a root, well, let's call it z0 root, implies that it's complex conjugate where you change from plus I to minus I or minus I to plus I is a root. Okay, so that's the conjugate root theorem, and you could use that here. That 3 plus 2i is a root. So 3 plus 2i, a root of this, implies that 3 minus 2i, a root. Then I need to know that you know about sums and products of roots. So if you've got a polynomial, quadratic, so say q of z is equal to z squared minus the sum of the roots plus the product of the roots. This is something I don't know if you still know this, but if you don't, you can do it this way. So what we have is that the sum of the roots, and then the other thing that's involved here, this has only got 2 roots, and they have to be 3 plus 2i and 3 minus 2i. So if you add these two together, the imaginary bits go away, and you get that minus the sum of the roots, which is minus 6. Add these two together, you'll get 6 is equal to p. One line. And then the product of the roots. Now, how you get clever about the product of the roots is that it's actually, if you multiply that by that, it's a difference of 2 squares. Kind of. Because it's a plus b by a minus b is a squared minus b squared. So if you do the product of the roots, which is q, this must be equal to, so do your little a squared minus b squared here, 3 plus 2i by 3 minus 2i. Okay, let me slow it down. 3 plus 2i, 3 minus 2i, that is equal to 3 squared, which is 9, minus 2i squared. And what's 2i squared? It'd be 2i by 2i, which is 4 by I squared, which is 4 by minus 1, which is minus 4. So you get 9 minus minus 4, 13. This way is clever. But you need more theory. But it's clever, there's no two ways about that. Okay. So what are we going to do now? We're going to go to the next question. What else would you do? Right, so what we have here is B part 1. So one of the things here is the more theory you know, the more that you understand it, the easier the questions should be. There's a lot of questions that if you understand quadratics very well, they become very, very easy. Stuff about symmetry of the graph, etc. And to be honest, how you learn about them is probably by doing questions. There's probably questions here and there and exercises, or exam papers that explore these different things. So one of the things about how the completing the square, something called completing the square for quadratics leads to the minus b formula. I'm sure that's in a past exam paper. I think the best way to learn is probably doing exam papers, especially the way I think the exam papers are set up now, where they're using the exam papers to teach you. So I teach, and I know if I want something to be, like I can talk in class and say, oh, this thing is important, or this has got an application here. If I don't put it on the exam paper, they don't care. So what I do is I put things that I want students to know on the exam papers, because of course future students will look at the exam paper, and I think that's what they're trying to do now. So if you want to learn, do exam papers. Okay, so what we got here, we've got some funny looking V. Don't really like this V, but anyway, V is equal to 2 minus 2 root 3I. And they're asking us to put it in a particular form, what's called the polar form, or cos theta plus I sine theta, where R is a real number. They could go a bit further. That R actually has to be a positive number, and theta is between 0 and 2 pi. Doesn't have to be, but okay. So this is another case where the more you understand, the better, I think. So this is a question I do with a picture. So the R is how far this complex number is from the origin, and theta is the angle that it makes with the positive x-axis. So we'll draw a picture. So this is in the argand diagram. So this would be real part, let's say of z, imaginary part of z. This is 2 along the real and negative along the imaginary. So the number is down here. So this is our V. And we want to find the R and the theta. So the R is fairly straightforward. We're just going to find that with some Pythagoras. That's R. And then theta is the angle it makes with the positive x-axis. There's the positive x, or the positive real axis, I should say. Right, so yeah, we can find R with a little bit of Pythagoras. Look at this little triangle. I think there's a formula for this, but when you've got the picture drawn, you may as well go at the Pythagoras. So R squared is equal to the sum of the squares of the other two sides. This is 2 squared. In the little formula, you'd have minus 2 root 3 squared, which makes it positive, but of course, as a length, this is 2 root 3. This gives you 4. This gives you 4 by 3 is 12, so it ends up being 16. And then you take the square root of both sides. Now, it's very important that you know this is 2 solutions plus, and where are they, plus or minus. But of course, R here, as I said, they could specify that actually R has to be positive. It is a length, so you can forget about that minus. And so R is square root of 16, which is 4. The angle, how would I make the angle? Well, how about I take 360 degrees, which is 2 pi, and take away this little angle here, alpha. And how will I find alpha? Well, I can find the tan of alpha is this length, which is 2 root 3, opposite over adjacent, which is 2 here. So let's write down that the tan of this alpha is opposite over hypotenuse, which is square root of 3, and okay, so let me do inverse tan here. Now, when you're doing differentiation, it's very important that you're in radians. Here it isn't so important, but the question is using 0 and 2 pi, so presumably they're talking radians, so we better do radians as well. So I make sure this thing is in radians. I'm trying to find alpha on its own, so I need to apply a function to both sides that gets rid of tan. I need to apply inverse tan to both sides. Now there are many solutions to tan alpha equal to root 3, but you're only interested in the one between 0 and 90, so the calculator is going to give you exactly what you need. Alpha is inverse tan of root 3. See what the calculator gives an interesting. So here's an example where if you put in square root of 3 as a decimal number and then do inverse tan, that's not a good idea. Keep the square root of 3. Yeah, it gives me a third pi, that's nice. And that means that the angle is 2 pi minus a third pi. So that's like two bits of 2 pi's minus a third of one of them. So that'll be what, 5/3 pi. The question has asked me to write this in a particular form. So let's do it. So V is equal to 4 cos 5/3 pi plus I sine 5/3 pi. Lovely. So let's see how we're doing for time. Next question. Using your answer here, find 2 possible. So we're looking for a W that squares to give you V, and I'm going to give you the real clever way of doing this. So you can go into your textbook and you can use something called the Moyers Theorem. And I'm sure you'll find lots of videos talking about the Moyers Theorem, but let me tell you something about how complex numbers actually multiply. So this is how complex numbers actually multiply. In particular, say if you square them. So this is how it works. Here's a complex number, say Z. Whoa, excuse me. Here is a complex number Z. And suppose it has a modulus of R and an angle of theta. So how complex numbers actually multiply, the way we do it by, multiplying 3 minus 2i by this number up here and multiplying it out, that's not the natural way that these things multiply. How they actually multiply is by doing stretches and rotations. So how it works is the stretching is done, you multiply the magnitudes together. So if you were to square this, or to square Z, you stretch it first, or you can rotate first, same thing. So the length goes from R to R squared. And then it rotates, you add the angles together, so it rotates through the angle theta. So the new angle formed is 2 theta, and this is where Z squared is. And so that means what you can do is you can actually do this question almost in your head. So the length now, should this be how you do it? I think possibly you can do this how your teacher shows you, but you check your answers with this. So this is a length of 4. So how do you end up with a length of 4? You start with a length of 2. So where you got W is the square root here. You know that the modulus of W must be equal to 2, because you're going to square W is going to be, the length is going to go from R to R squared, 2 to 2 squared. Now, we have to double. Now I'm going to break a habit of a lifetime, and I'm actually going to go into degrees here. So 1/3 pi is 60 degrees. This is 300 degrees all the way around. Okay. Now, how can you double an angle to get to 300 degrees? Now, the first way of doing it, so I think this thing is called, well, we'll call it theta 1 rather than argument 1, is 150 degrees. That will do it. If you double 150 degrees, you'll get 300 degrees. That'll work. Now, that'll be half of this, which will be 5/6 pi. Now, where's the other one? How do you double to get 300? Well, this is the clever bit. If the argument is very, very big, the angle is very, very big, for example, even if you square V, it's at 300 degrees. So you rotate, the first one is you rotate once, and then to square it, you'll go around to 600 degrees. And then you take away a multiple of 360 and you get 240. So what we need is something that has got such a big angle that it rotates around twice, or actually even cleverer. No, I can't do the other one. So actually basically what you need is something that, let's say, we need the angle plus 360 degrees, that it's gone around once and a little bit more, and I need a different symbol here, say theta 2, yeah? That gives you 300 degrees. think the 360 is in the wrong place, isn't it? That's 660, so theta is 330. Now think about 330 degrees. So start at 0, do 330 degrees, and do 330 degrees again. That's the square, and you get 300 degrees. So you can actually write, so you end up with the other angle is 330, which you can convert to, I think it's going to be 11 pi over 6. Now it's a little bit unfortunate because we've done this question essentially in our head, which is probably not that advisable for you to do it. I just think it's a nice thing to see. You could do, I think if you want to see more of this, Google geometric the Moyers Theorem. It should actually give this. Now we haven't answered the question that's asked. We have used the answer to the previous part. Because I knew that this, had to square to give me 300 degrees, or double to give me 300 degrees, square to give me 4. So I did use it, but I haven't given the answers in the correct form. So let's say W1 is equal to R2 cos of 5 pi, the first angle 5 pi over 6, plus I sine 5 pi over 6. And then I'll probably actually use my calculator here, which I'm not mad on, but anyway, 2 by cos 5 pi over 6 is minus root 3. And then I'll just go into the calculator and change the cos to sine. I get plus 1 by I. And then the other one, so this would be an example actually, because if you look at z squared minus v equal to 0, that is a quadratic. But the conjugate root theorem, you won't get minus root 3 minus I, because, not guaranteed, because the v is not a real coefficient. So that's why that doesn't work. So W2 is 2 cos 11 pi over 6, I seem to have. I think I'm going to be using my own words in a moment, because this one is minus I, and this one that's okay. Oh yeah, there's another way of going about this as well. So you have, okay, there's actually an even cleverer way to look at this. So the easy one was with the length of 2 and the modulus 5 pi over 6. So W squared equal to this yoke does give you the V that you wanted. And what you can do is you could actually multiply this by minus 1, which of course is this yoke. That will also equal W squared, which is V. So W and minus W would be the two roots. Okay, is that enough? I think, yeah, we have written the answers in the right form. You'd have to have a serious think about whether you should do this question like that. You would get the full marks, there's no two ways about it, but there's probably a bit of work to get to there. Okay, thank you.